everyone, welcome to today's lecture. We are going to go over Newton's laws of motion. So the first thing we need to know or understand is the idea of forces, okay? And to understand what a force is, we first had to study kinematics, or the study of motion, and dynamics, the study of how forces affect the motion of objects and systems. Dynamics considers the causes of motion of objects and systems of interest. So in kinematics, we just looked at how to analyze a system, what's going on, what's the motion. Now we're going to be able to take into account what is causing that motion, okay? So a force is intuitively a push or a pull, okay? And it does have a magnitude and direction, so it is a vector, okay? And when we're going through this, you'll see me, or you'll see a lot of these diagrams. They're called free body diagrams, and they are really just a sketch showing all the external forces that are acting on an object or the system, okay? So this is an example of the diagram that you first initially draw, okay? So we have three figure skaters here, and we have one that's stationary, and then we have two other figure skaters that are just pushing her along. Okay, so we have forces in two different directions here. Okay, so if this was the XY axis here, okay, we have that F1, the first force is being applied in the X direction, and the second one is being applied in the Y direction. Okay, and then from these two forces, we can use the tip-to-tail method to find the F total force, okay, of the system here. And this is like what we've been doing with vectors in the past of our motion, okay? And now we can take this even further and draw a free body diagram of this. Okay, so this shows you the two forces that are involved in our system, okay, and we can say that this is our point of interest or our object of interest. Okay, so that's the main idea, that we need to first kind of lay down that path in order to talk about Newton's laws. Okay, I'm going to talk about this a bit later as well, but this is just kind of the general idea of how to draw a free body diagram. We'll get into more examples towards the end of the lecture. But basically, you want to draw the object that you are taking into consideration, and include all the forces, resolve these forces into X and Y components, and then draw a free body diagram for each object in the problem. Okay, so this is a box at rest on a horizontal surface. We just have the box sitting here. This is our little diagram. And then we can convert it into a free body diagram showing these different forces. Now, I'm not going to go over what these are at the moment, but we will get into this in a little bit later. Okay, so let's go ahead and move on to more forces. Okay, so we have two main types of forces. We have contact forces, which are going to be any type of forces that are due to direct physical contact between objects, and that's what we will see a lot, okay, in this course at least. And then we have field forces, which are going to act without the necessity of physical contact between the objects. So an example of contact forces would be like the floor, or a person's feet on floor, okay, and then a field force would be like Earth's gravitational field. Okay, and again, we will look more into the contact forces. In this course, the only field force that we will really be looking at is Earth's gravitational field. Okay, so we have here an example of this guy sitting here. We have a couple of different systems of interest. Say we're interested in just him and the chair. So he is acting on the chair, with some weight, W, and the chair is acting back on him with this C force, okay, or this contact force, okay? So we're going to get into a little bit more how to figure out where the forces are and what forces you'll need to label and such in a few minutes here. Okay, so a force has units, okay, and the units are in newtons or big N, okay. This is the force that's needed to accelerate an object with a mass of 1 kilogram at a rate of 1 meters per second squared, okay, or we can say 1 newton equals 1 kilogram 1 kilogram meter per second squared, okay. So this is the unit of force, okay. We can break a force down into its components. So we can say that F bar is equal to A I hat plus B J hat plus C K hat. Okay, so this is going to be the force broken down into its three components, in X, Y, and Z. Okay. We can also just have them a force that's in 2D. Okay, so F would be like A I hat plus B J hat. Okay. But this is more universal. We also have net external force, which that'll be all of the forces that are being applied to or the object that's applying the force externally. Okay, so this is going to be equal to the sum of all of the forces. So it would be F1 plus F2 plus ... Okay? All right. So Newton's first law of motion, that's going to be the idea that a body at rest remains at rest, or if it's in motion, it remains in motion at a constant velocity unless it's acted on by a net external force. Okay, so an example of this would be like a football sitting on a tee. Okay, that football's not going to move unless there's some kind of force acting upon it. Okay, so now once that football is kicked, it will continue forever in that direction until it is acted on by another force. So an example would be like gravitational force or friction, like air resistance. Okay, so that's Newton's first law of motion. Okay, so something will stay at rest unless it is acted on by another force, or it'll stay in motion unless it's acted on by another force that will slow it down. Okay. Okay, so I have quite a bit of information on this slide, so I'll try to kind of go over each individual point a little slowly. Okay, so this is the ideas around gravitation and inertia. So first of all, we need to consider the term mass. What do we mean by mass? Because a lot of the time, when we look at mass, we are thinking in our heads that it's the weight of something, right? That's kind of a misconception. Mass is a little bit different. Mass is the measure of the amount of matter in something. Okay, so it's not going to be the weight of something, it is the amount of matter in something. Okay, weight is going to be a force, and we'll talk about that in a few slides here. Okay. Gravitation is the attraction of one mass to another. So like the attraction between you and the earth that holds your feet to the ground. Okay. Inertia is the ability of an object to resist changes in its motion or to resist acceleration. Okay, so that's inertia. Newton's first law is also known as the law of inertia. Okay, so keep that in mind. And inertial reference frames are a reference frame that are moving at a constant velocity relative to another inertial frame, and that is also inertial. Okay, or a reference frame accelerating relative to an inertial frame that is not inertial. Okay. So we're just saying that, remember when we were talking about reference frames, you just kind of want to understand what is going on in those different reference frames and being able to relate that to the motion and so on. Okay. Oh, this should be up here. Going back to the idea of mass, okay. Which one has more mass? A kilogram of cotton balls or a kilogram of gold? Which one has more mass? Okay, so you might be thinking in your head, well, one is denser than the other, right? The gold is denser than the cotton balls, so the gold must be more massive. But that is incorrect. Mass, remember, is a unit of measure of matter, and mass is measured typically in kilograms. So which one has more mass? Kilogram of cotton balls, kilogram of gold, they're the same, right? Okay. So Newton's first law and why we care about it. Because a lot of times you get all of this stuff in your head, like I just talked about all this stuff, and you're kind of like, okay, well, do we care about this? Like, why does it really matter? Well, say you are in a vehicle, like this giraffe here, driving along, and then you hit a wall, and that wall stops your car. Well, your body is still going to be moving. You still have that inertia. You still have that force to go forward. Okay, so that's why, or that's one of the reasons why we care about understanding physics and Newton's laws. Okay, because if we're this giraffe right here, we need to wear a seatbelt. Okay, even a human, we need to wear seatbelts or else we're going to be flying forward through that car. Okay? Alright, so Newton's first law and equilibrium. Remember that equilibrium is the state at which forces on the system are balanced. So everything should be in balance with each other. Okay? This tells us that the net force is going to be equal to 0. Okay, that's what an equilibrium means. Also, the velocity is constant at equilibrium. Okay. All right, so let's move on to the idea of forces and acceleration. Now, I'll only be able to start this in this video, but I'll continue in the next one. So from the first law, we saw that the net external force causes a non-zero acceleration. Okay, a net external force causes a non-zero acceleration, and external forces affect, the system of, the motion of a system. Okay, so from Newton's first law, we can now derive Newton's second law. Okay, so again, we know that the acceleration is somehow proportional or somehow related to the net external force, and our acceleration is somehow related to the inverse of the mass. And I'll talk a bit more about that in the next video.